Welcome to this model, and this model let us have an insight of frisk transmission equation. The diagram below shows the general radio system link where the PT is the transmit part, GT is the transmit antenna gain, and GR is the receive antenna gain, and PR is the receive power. R is the distance between the transmit and receive antennas. Okay, and the power density radiated by an isotropic antenna can be given as S average is equal to PT by 4 pi R square W by M square. Okay, and this result reflects that fact that we must be able to recover all the radiated power by integrating over a sphere of radius or surrounding the antenna, since the power is distributed isotropically, and the area of the sphere is 4 pi R squared, and if the transmit antenna has a directivity greater than 0 dB, we can find the radiated power density by multiplying the directivity, since directivity is defined as the ratio of actual radiation intensity to the equivalent isotropic radiation power intensity. And in addition, the transmit antenna has losses. We can include the radiation efficiency factor, which has the effect of covering the directivity, converting the directivity into gain. And this general expression for the power density radiated by an arbitrary transmit antenna may be given as S average is equal to GTPT by 4 pi R square. If the power density is incident on the receive antenna, we can use the concept of effective aperture area to find the received power. Then the received power can be written as E into S average, which is GTPT AE divided by 4 pi R square. And this equation can be used to relate the effective area to the directivity of the receive antenna. Again, the possibility of losses in the receive antenna can be accounted for by using gain, that is gain of the receive antenna. Then the final result will be the received power will be GTGR lambda squared by 4 pi R the whole squared into PT watts. Okay, and this equation is known as the frisk equation, and the factors which reduce the received power are impedance mismatch at either antenna or polarization mismatch between the antennas, and propagation effects leading to attenuation and depolarization, and multipath effects. So you can observe that the received power decreases as 1 by R squared as the separation between transmitter and receiver increases. This dependence is a result of conservation of energy. While it may seem to be prohibitively large for large distances, in fact the space decay of 1 by R squared is usually much better than the exponential decrease in power due to losses in a wired communication link. This is because the antennas of power on a transmission line varies as e power minus 2 alpha is z, where alpha is the attenuation constant of the line, and at large distances the exponential function decreases faster than algebraic dependence like 1 by R square. Thus for long distance communication, radio links will perform better than wire links. So this, and even fiber optic lines, and it is based on the repeaters can be inserted along the link to recover the lost signal power. As you can see from the first formula, the received power is proportional to the product of product PT into GT, and the two factors, that is the transmit power and the transmit antenna gain, mainly characterize the transmitter. In the main beam of the antenna, the product PT-GT can be interpreted equivalently as the power radiated by the isotropic antenna with the input power PT into GT. So the equivalent effective isotropic radiated power is given by EARP is equal to PT into GT. For a particular given frequency and range, the receiver antenna gain, the received power is proportional to the EARP and can only be increased by increasing the EARP. And this can be done by increasing the transmit power, the transmit antenna gain, or both. Next we'll look it into link budget and link margin. The various terms on the frisk formula are often tabulated separately as a link budget, where each of the factors can individually consider in terms of its net effect on the received power. So additional loss factors such as line losses or impedance mismatch at the antennas atmospheric attenuation or polarization mismatch can also be ordered in the link budget. One of the terms in the link budget is the path loss, accounting for the free space reduction in input signal strength with the distance between the transmitter and the receiver. The path loss is defined as the L0 as 20 log of 4 pi r by lambda, which is greater than 0. You can note that the path loss depends on wavelength, which serves to provide a normalization for the units of distance. For example, with the above definition of path loss, we can write the remaining terms as transmit power as PT and transmit antenna loss as minus LT, transmit antenna gain as GT and path loss as minus L0 and atmospheric attenuation as minus LA, and receive antenna gain as GR and receive antenna line loss as minus LR, and the last received power as PR. So PR is equal to PT minus LT plus GT minus L0 minus LA plus GR minus LR. So we have also included loss terms from atmospheric antennas and line antennas in this equation. Assuming that all the quantities are expressed in dB, now we can write the received power like the equations was I said earlier. If the transmitter receiver antenna is not impedance matched to the transmitter receiver, then the impedance mismatch will reduce the received power by the factor 1 minus tau square, where tau is the reflection coefficient and the resulting mismatch loss is given by L impedance is equal to minus 10 log of 1 minus tau square. This can also be included in the link budget to account for the reduction in radiation power. Another possible entry is the in the link budget relates to the polarization matching of the transmitter and receiver antenna. As a maximum power transmission between transmitter and receiver requires both antennas to be polarized in the same manner. And if a transmit antenna is vertically polarized, for example, and maximum power will be delivered only when to a vertically polarized receiving antenna, while zero power will be delivered to horizontally polarized receiving antenna, and half of the available power will be delivered to circularly polarized antenna. And in practical communication systems, it is usually desired to have a received power level greater than the threshold level required for the minimum acceptable quality of service. So, and the link margin is defined as the difference between the design value of received power and the minimum threshold value of the received power. Link margin is PR minus PR minimum. Link margin should be a positive number, and it may vary from 3 to 20 dB. And the reasonable link margin provides a level of robustness to the system to account for variables such as signal fading due to weather or movement of mobile user, multipath propagation problems, and other unpredictable effects that can degrade system performance and quality of service.